Hi, I'm very happy to have this opportunity to present our work, PACE, a passive acoustic localization system. PACE is able to passively locate and identify multiple targets simultaneously based on the footsteps it generates. Essentially, a footstep contains rich acoustic components. The one that propagates through solid medium is called structure-borne component, and we use it for ranging. The one that propagates through air is called air-borne component, and we use it for angle of arrival estimation and identification. Combining the ranging and angle of arrival information, we thus can locate and track a target with just a single acoustic beacon. We now present more details on acoustic physics behind PACE. Here we show a snapshot of footstep that contains structure-borne and air-borne acoustic signals. The speed of structure-borne component travels around 3,000 meters per second, and air-borne one is only about 340 meters per second. This sharp difference in propagation speed allows us to readily separate them. As shown in this figure, we can extract the preceding few examples as structure-borne signals and use the remaining as air-borne signals. The structure-borne component in solid medium exhibit acoustic dispersion properties, where high-frequency components travel faster than low-frequency ones. This acoustic dispersion phenomenon carry range information. Meanwhile, using airborne signals for angle of arrival estimation via beamforming has become a well-investigated topic. Therefore, with range and angle of arrival, we can thus locate and track a target. To identify a target behind each footstep, we use airborne signals that contain richer features. However, to implement the above system entails two challenges. First, the environmental heterogeneity can significantly aggravate the range performance. As revealed by this equation, the propagation speed of each acoustic component not only depends on the frequency, but also the properties of material, including the elasticity, stiffness, and thickness. This indicates that the structure-borne acoustic profiles generated by the same person on a wood floor would be quite different from that on concrete ground. The same problem goes for airborne signals for identification, as the generated footstep would be quite different under high heels and sneaks. Second, footstep is often of low volume, hence pose significantly challenges in angle of arrival estimation. It suffers from severe indoor multipath and strong acoustic noise background, making existing solutions infeasible. To solve the environment heterogeneity problem, we develop a neural network with adversarial training. It mainly consists of three parts: a feature extractor, a range estimator, and a domain discriminator. The feature extractor transforms an input footstep waveform into a lower dimensional feature vector. Using this low dimensional feature vector, the range estimator aims to infer an accurate distance, while the domain discriminator tries to identify different domains. The input to the domain discriminator is a weighted feature vector, whose weights are extracted from the range estimator. The ultimate goal of this network is to obtain a domain-independent feature vector so as to achieve an accurate range estimation and cheat the domain discriminator to fulfill its task. It is this domain-independent feature vector with only range-specific features that enables a cross-domain generalization. To tackle the second challenge, we propose a new spectral weighting function. This function allows to obtain more sharper correlation peak with low volume inputs, hence can notably improve beamforming performance for angle of arrival estimation. As we can see from these two figures, with our spectral weighting, it can achieve sharper correlation peak and better beam pattern. To identify a target, we utilize the male frequency septural coefficients of airborne signals. As we can clearly see in this figure, the male frequency septural coefficients features of different persons exhibit noticeable distinctive features, thus facilitating user identification. To exclude domain information such as different shoes or floor materials, we also use domain adversarial training. We further enhance the identification accuracy with center loss. This is the hardware platform that we used in our experiment. It is a circular arrow with 6 microphones. We attach it on the ground tightly to capture footsteps. Now let's check the performance. The green curve plots the ranging performance under different environments with domain adaptation, while the blue one is without. It is observable that domain adversarial training can improve cross-domain ranging performance. Meanwhile, when we apply captured data from other environments that have never participated in the training process, we can also achieve adequate ranging performance. As we can see from the figure, the red curve shows the ranging performance with new samples that have not participated in the training process. It has similar performance with the green one. We now check the angle of arrival estimation performance. The left figure shows the angle of arrival spectrum when there are 5 footsteps simultaneously captured. As we can see from the figure, the peaks which indicate the angle of arrival are highly consistent with ground-truth ones. In the right figure, we can see that the maximum angle of arrival estimation errors are within 10 degrees, even under concurrent 5 acoustic sources. This salient performance is accurate enough for our localization purpose. We now see the identification performance. As we can see from the table, we can achieve a maximum of 96% identification accuracy. And during our experiment, we found that the adoption of Chen laws can boost the identification performance by as far as 12%. We have also checked the tracking performance under multiple persons, as reviewed by the 2 figures. Pace can accurately track multiple targets and do not mix their traits even their trajectories are overlapped, thanks to this ability to distinguish multiple targets. That's all for our presentation. Thanks for listening.